Hi folks, we're going to take a look at question 2 from the Unit 7 quiz. So here we're given a rectangular piece of cardboard with dimensions 60 by 30, and we're going to make a rectangular box with an open top, and we want the dimensions which give the largest volume. Okay, so let's start with what we're given, which is a rectangular piece of cardboard. So here's my piece of cardboard, and what I want to do is create an open top box. Okay, and the way to do this by wasting the least amount of material is to cut square pieces from each corner, okay, of the same size on each of the four corners, okay, so that then we lift all these four little flaps up, and it's going to create the same height, okay, and all we're losing are these four corners, okay. So what we don't know is how big a corner we're going to cut off, so we'll make that our variable. But of course, if that's x, then this will be x, and this will be x, and this will be x, and so on and so forth. Okay? Now, what we're trying to do is we're trying to maximize the volume of this box. So that's where we're going to put our attention towards. So here, the volume is given by length times width times height. And let's see what the dimensions of this box are going to be. Well, the height, clearly, if I move this flap up, is going to be x. So the height will just be x. Okay. The length of the box will be that dimension there. And if this is 60 and that's 30, then this part here would be 60 minus the x's that we're removing on each side. So the length will be 60 minus 2x. And similarly for the width, okay, the total here is 30, and we're removing an x on either side. So the width is 30 minus 2x. Okay, and so now we'll use this to create an equation for the volume. Okay, so length times width times height. So we've got 60 minus, 2x times 30 minus 2x times the height, which is x. So what we have now is an expression for the volume, and it's already given in terms of one variable. So this is ready to go. We have our model. Maybe before going on to do the calculus portion, let's figure out what restrictions we have on x. So clearly x has to be strictly greater than 0, because if you're not cutting anything off, there's no height to this box. So we know x is going to be strictly greater than 0. And I guess if we're looking for an upper limit, we really should be focusing in on that smaller side. Okay, so we definitely can't have x be more than half the length, so it would be 15. Okay, because if x were equal to 15, you'd just be folding the sheet in two. You wouldn't actually be creating a box, so it has to be strictly less than 15. Okay, so notice here that we do not have a closed interval, so we're not guaranteed a maximum, but hopefully we will be able to find one. Okay, so before differentiating, I strongly suggest you do not try to use the product rule twice here to differentiate this. If you just expand it, you'll get a nice, easy polynomial to differentiate. Okay, so let's start here. We've got 60 times 30, so that's 18 with two zeros, 1800. Okay, here you've got 60 times 2, so negative 120. 2 times 30 is 60, so negative 120 minus 60 will be minus 180x. And then here you've got negative 2 times negative 2, so plus 4x squared. And all that is being multiplied by x. And so my final function here will just be, and I'll put it in order of exponent here. So we've got 4x cubed, okay, and then we've got minus 180x squared, and then plus 1800x. Okay, and so now this would be the right time to take our derivative. Okay, so v prime, derivative v with respect to x, is just going to be 12x squared minus 360x, and then plus 1800. Okay, so I would say we're going to be setting our derivative to 0, but let's try to make life easier for each other. See if 1800 is perfectly divisible by 12. So 1800, and I believe it is, divided by 12 is 150. Okay, so I will be setting this to 0. And in the same step, what I'll do is I'll divide both sides by 12. So 0 divided by 12 won't change the left-hand side. So now I'm left with x squared, 36 divided by 12. So that'll just end up being 30. So minus 30x. 3 times 12 is 36. And then we saw that this is going to be plus 150 from my check earlier. Okay, so you might take a really quick look at this to see if it factors nicely instead of using the quadratic formula. And here, I don't know, if, 50 times 3, that's not going to work. 30 times 5, that's not going to work. And that's as far as I'm going to go. Okay, so might take a quick look at factoring, but otherwise, I'll just go straight to solving this equation with the quadratic formula. So negative 30, so that's 30 plus or minus the square root of negative 30 squared minus 4 times 1 times 150. Okay, all divided by 2a, so all divided by 2. So here x is equal to 30 plus or minus, and let's calculate this b squared minus 4ac, so 30 squared minus 4 times 150. Okay, 300, so we will have solutions here. And divided by 2. Now, since this is an application question, I'm going to approximate these answers. So let's see if both of them are valid. 30 plus the square root of 300 equals, and then divided by 2. So that is 23.66, or we've got 30 minus the square root of 300 equals divided by 2, okay, 6.34. Okay, so we take a look at our answers. They are both positive. However, 23.66 does not lie within our domain. Okay, so we are going to eliminate that answer, but 6.34 does lie within the domain. Okay, so this is our only critical point. So we're going to have to hope that it is a maximum. Okay, so we'll have to test that out. We'll have to test v prime before and after 6.34. So if we go to v prime here, okay, say we stick in x is equal to 1, so 12 minus 360 is going to be some negative number, but when we add 1800, that will definitely be positive. I don't even need to check that. Okay, let's pick something above 6.34, but below 15. So let's say we take say 10. So let's calculate that there and see what happens. So we've got 12 times 10 squared is 100. Okay, minus 360 times 10, and then plus 1800, and that still comes out to be negative. Okay, so we are going from positive to negative, hence 6.34 does refer to a maximum. Okay, now let's remember what our steps are. Step number 1, to use a diagram and equation to come up with a model, figure out the constraints on the variable being used. Then we do our calculus to work out where the critical points are, and if we have a maximum in this particular case, and we do. Now let's see what the actual question is. So here it says find the dimensions of the box, which will have the largest volume. Okay, so here we're not just looking for the value of x, but all 3 dimensions. So we know that the height, well, that's just given by x, so the height will be 6.34, and this was centimeters. Okay, the length is going to be given by 60 minus 2 times 6.34. Okay, so the length will be given by, so 60, oops, make sure you can see that, 60 minus 2 times 6.34, so the length will be 47.32 centimeters, and then the width will be 30 minus 2 times 6.34, okay, which will calculate 30 minus 2 times 6.34. That is 17.32 centimeters. Okay, so again, please make sure that once you've actually finished all your algebra, finish the calculus, make sure you're actually answering the question that is being posed. Okay, that's it for this one.